section 2.2, all about matrix inverses. So let me just talk about real numbers for a moment. 5 times a fifth is the same as a fifth times 5, which is 1. So we call 1/5 the multiplicative inverse of 5. Now for matrices, it's the same idea, except instead of getting 1, we're going to get the identity. Now I'll talk about the definition in a second, but let's just look at this example. If I multiply these two matrices, remember how that works. I'm going to take this row and dot it with this column to get 1. And then I'll take the second row in the first matrix, dot it with that first column, and that's going to give me 0. And then I'll ignore the first column in the second matrix and look at the second column and do those same dotting operations, and I'm going to get 0, 1. So if I call this matrix A and I call this matrix C, C times A is the identity. And you can verify that AC is also the identity. So in that case, we call C A inverse, and we say A is invertible or non-singular. That's another term for invertible. Now, next time, we will see that if A is square, we only need to check multiplication on one side. We need to check AC is the identity. Just like 5 times a fifth is 1, that automatically implies that a fifth times 5 is 1. If a matrix is invertible, then the inverse is unique. And you can read through that simple proof right here. 2 more big results are right here, and I'll let you read those. We'll talk about Theorem 5 in a minute, but don't worry too much about all the facts we're going to learn today, because we're going to summarize those in the next section in a big proof called the invertible matrix theorem. So let's talk about the inverse of a 2 by 2 matrix. It's a very easy formula. If the determinant of A is not 0, now the determinant is the number AD minus BC, then A is invertible. And here's a formula for the inverse. You take 1 over the determinant, and then you switch the A and the D, and you make the B and the C negative. And my mnemonic device for that is dancing, that's the D, naked bears, that's the negative B, and then on the second row, never cause, that's negative C, A, accidents. So let's try that formula out on this matrix here. And this is the matrix that we had above that we called A. So we already know the inverse, but let's use the formula. A inverse is 1 over the determinant. The determinant is 14 minus 15. And then I switch the A and the D, so negative 2, negative 7, and I make the off-diagonal entries negative. Negative 3, negative 5. That's 1 over negative 1, which is negative 1. And then negative 2, negative 3, negative 5, negative 7. That's 2, 3, 5, 7. And indeed, that's the matrix that we called C above. So C is A inverse. Now, let's use Theorem 5 to solve this system. Theorem 5 says that if A is invertible, then the equation AX equals B is consistent, and the unique solution is X equals A inverse B. Okay, well, this linear system is not random. This is the exact matrix A that we had above. This is X and this is B. And so by Theorem 5, we have X equals A inverse B. So that's X1, X2. We found A inverse. A inverse was 2, 3, 5, 7, and B is 2, 1. And when we multiply those two things out, we get 7, 17. So that's our unique solution. Now in practice, this is not how you want to solve a linear system. Unless you're given A inverse, this is going to be a lot of work. In practice, the way you would want to solve this linear system is just to reduce the augmented matrix, like we've been doing since day 1. Okay, properties of inverses. If A and B are invertible, the inverse of the inverse is A. That makes good sense. A times B is also invertible, and the inverse is the inverse of each matrix in opposite order. So it's important to change the order, and so let me just show you how that works. If I take AB and I multiply by AB inverse, according to number 2, AB inverse is B inverse A inverse. Remember, matrix multiplication is not commutative, so you can't just move these matrices around. But I don't have to, because now I've got B inverse A inverse sandwiched in the middle. That's the identity. But the identity times A is A, so now I've got A inverse. which again is the identity. 3 tells us how inverses and transposes interact. And then number 4, we'll look at in a minute, the inverse of RA is 1 over RA inverse. And there's no property for A plus B inverse, because even if A is invertible and B is invertible, A plus B might not even be invertible. So those are a lot of properties. Let's compare those with the properties we learned about transposes. So you might want to pause the video and just see if you can recall for each of these properties if there was a similar property for transpose and what it was. All right, for number 1, yes, there was a similar property. If you took the transpose of a transpose, you got your matrix back again. Number 2, again, very similar. AB transpose was the product of the transposes in the opposite order. B transpose, A transpose. Number 3, well, I'm just going to write same because it already relates inverse to transpose. And number 4, the property there was RA transpose was simply R times A transpose. And then for property 5, whereas A plus B inverse has no property, there was one for A plus B transpose, and it was just A transpose plus B transpose. So let's take a look at property 4 for inverses and transposes a little bit more carefully with a very easy example. So I've got A equal to this matrix, and I use my dancing naked bears to find A inverse, and you should verify that's A inverse. And then for A transpose, remember how that works. You just interchange the rows and the columns of A, and so there's my A transpose. Let's look at 2A quantity transpose. So I took the matrix A and I multiplied each entry by 2, and now I'm going to take the transpose. So 4, 6, the first row becomes the first column, and then 2, 4 becomes the second column. Now that's twice 2, 1, 3, 2. Which is exactly twice A transpose. All right, now let's look at that property for inverses. Again, I multiplied A by 2, and now I want to find the inverse. So I'm going to use my dancing naked bears. Well, I want 1 over the determinant, 1 over 16 minus 12, and then I'm going to switch the A and the D, which are both 4 anyway, and make the B and the C negative. Okay, well that's 1 over 4, 4, negative 6, negative 2, 4. Now what I'm going to do is think of a fourth times a half, and I'm going to distribute 1/2 into this matrix here. So I'm going to leave a half out and divide each entry of this matrix by 2, giving me 2, negative 3, negative 1, 2. Well, that's exactly 1/2 A inverse. Okay, the algorithm Dancing Naked Bears for finding an inverse only works for 2x2 matrices. So what do you do if you have a 3x3 or a 4x4? By the way, one important thing I forgot to mention at the top, but it is written down. You can only talk about invertible matrices for square matrices. Only square matrices will have inverses. Okay, so the algorithm for finding an inverse, if a square matrix is invertible, is right here. You augment A with the identity, and you try to reduce that to the identity on the left. If you can, then A inverse will be on the right. If at some point you get a row of zeros on the left, you can quit, because a row of zeros will never become the identity, and A is not invertible. So let's see an example of how this works. I've got the matrix A here, and I want to find A inverse. So what I do is I put A on the left, and I augment with the 3x3 identity on the right. And now I'm going to reduce and see if I can get the identity on the left. So this won't take long. It's going to take 2 operations. The first thing I want to do is kill this negative 3. So I'm going to leave row 1 alone, and then I'm going to replace row 2 with 3 row 1 plus row 2, which will give me 0, 0, 1, 3, 1, 0. I'll leave row 3 alone. Okay, I'm almost there. Now to get the identity on the left, I just need to swap rows 2 and 3. Okay, I've done that. And now I've got the identity on the left. And so this must be my A inverse. So my A inverse is the 3x3 matrix 1, 0, 0, 0, 0, 1, 3, 1, 0. The only thing tricky about this algorithm is that the rows can get very long, and so you have to remember to do the row operation all the way across the row, and so the arithmetic can get a little bit tricky. Last topic, elementary matrices. Elementary matrices actually justify that algorithm we just used, but they're very interesting in their own right. So first, let's talk about the definition. An elementary matrix is a matrix you get from the identity matrix by applying one row operation, only one. So here are 3 examples. In this first matrix here, what I did to the identity to get this matrix is I multiplied row 2, I scaled row 2. So I took row 2 of the identity and I got that matrix. So that must be an elementary matrix. The next one's also elementary because what I did to the identity to get that matrix is I swapped rows 2 and 3. And then this third one is elementary because what I did to the identity to get that matrix is I replaced row 3 with 3 row 1 plus row 3. All right, let's look at these 5 matrices here and see if they're elementary. So you might want to pause the video and just see if you can determine if these are elementary matrices. Okay, this first one, this is an absolute yes. I took row 3 of the identity and I replaced it with -3 row 1 plus row 3. The second one is a no. This required 2 row operations, a scale and a swap. That's not allowed. You can only do 1 row operation. Third one is super easy. No, you can't have a non-square matrix. An elementary matrix has to be square because you get it from the identity matrix. Third one, this is a yes. I just swapped rows 3 and row 1. And this last one, again, is a no. There were 2 operations going on. That was a scale of row 1 and a swap of rows 2 and 3. Okay, here's why we love elementary matrices. Take a generic 3x3 matrix, A, and let's multiply it on the left by the 3 types of elementary matrix. So in my first example here, I took a scaling elementary matrix, scaled row 2 by 2. Multiply by the matrix A, and look at what it does to A. It scaled row 2 by 2. So it did to A exactly what I did to the identity to get E1. That's not a coincidence. All right, let's look at the second example. The second example, I took the elementary matrix I got by swapping rows 2 and 3, and I multiply by A. Look what it does. It swaps row 2 and 3. Pretty neat. You can kind of guess what's going to happen on this next one. This elementary matrix E3 I got by replacing row 3 by 3 times row 1 plus row 3. Well, when I multiply by A, that's exactly what it does to the matrix A. It replaces row 3 with row 3 plus 3 row 1. And so I've written that out in words right here. Okay, another cool thing about elementary matrices is that they're invertible. And that's because the elementary row operations are reversible. So let's see how to find an invertible elementary matrix. So in this first example, E1, the way I got E1 is I multiplied row 2 of the identity by 2. How would I undo that? Well, I would multiply row 2 of the identity by a half. So 1, 0, 0, 0, a half, 0, 0, 0, 1. That would be the inverse of E1. The inverse of E2, how would I undo swapping? Well, I would re-swap. So actually, the inverse of E2 is E2 itself, because you're just going to re-swap. 0, 0, 1, 0, 1, 0. And you can verify these. You multiply E1 by E1 inverse, and you can see that you'll get the identity. All right, and finally, E3 inverse. How would I undo replacing row 3 with 3 row 1 plus row 3? Well, I would go like this. 1, 0, 0, 0, 1, 0, -3, 0, 1. I would add -3 row 1 to row 3, and that would undo what I did. All right, and finally, another big theorem that we will talk about next time, it will be part of the invertible matrix theorem. An n by n matrix is invertible if and only if it is row equivalent to the identity. All right, and that is the end of this section.